Warning, the video you're about to watch contains mathematics at the level of college algebra and trigonometry. All material has an assumed prerequisite of both Algebra 1, which is elementary algebra, and Algebra 2, which is intermediate algebra. While some prerequisite topics are reviewed briefly, a more thorough review of these entrance topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, Professor of Mathematics at Cosumnes River College in Sacramento, California. In this video, we're going to derive the base graphs for the tangent and the cotangent. Rather than repeat everything that I already did in the video on the derivation of the secant and cosecant functions, I'll just remind you. Definition of a vertical asymptote. We're going to need that. So a function is said to have a vertical asymptote at x equals a if the function values tend to positive or negative infinity as x approaches a. And that is either from the left or the right or both. Doesn't really matter. And if you need a description of that or a deeper description, please see my video on deriving the secant and cosecant graphs. Also mentioned in that same video that the tangent is an odd function, and so therefore the cotangent is also an odd function. And let's see, anything else that I have in this? Nope. This theorem here is going to be kind of important for us. So the periods of the tangent and cotangent function are pi. This is critically different than the sine, cosine, secant, and cosecant. All the other trig functions have a period of 2 pi, but it turns out the tangent and therefore the cotangent, they have periods of just pi. And the reason why is, this is not going to be a proof, it's going to be more of a justification. The reason why is because of the way that they're defined. If you think about the tangent, let's just deal with the unit circle definition of the tangent for now. So we have the unit circle, the tangent of an arc length on the unit circle. Let's go ahead and get to a point here. So let's just pretend as though this is the point we're talking about, x comma y. So what's the tangent if this is the arc length t? And as we know, if that's the arc length t on the unit circle, then the angle is also t, again, on the unit circle. The tangent is defined to be y over x. Now, if you think about that, here is the y value and here is the x value. So in reality, what the tangent is really giving us is rise over run. It's actually giving us a change in y over a change in x. Why do I say that? Because technically this line that we call the radius here, this line segment, I guess you could say, it connects the 2 points x comma y and 0 comma 0. The slope of that line would be the difference in the y values, y minus 0, over the difference in their related x values, x minus 0. And that is y over x. So that is the slope of that line. So tangent is truly just the slope of our line emanating from the origin out to the edge of our circle where our point is, which is what we're referencing to build all of our trig functions. Now that we've mentioned that, because that's kind of an important point to make before we continue our conversation. So now that we mentioned that, let me go ahead and bring in a ruler here. And I'm just going to use the ruler to showcase the slopes. So notice right here, the slope right on the x-axis is going to be it's going to be 0. I just didn't use a ruler to draw this, but it's going to be a 0 slope. But then let me pin this down here. As you increase the angle, that slope is going to be steeper. This might be a slope of 1, but all of a sudden it becomes a slope of 2, 3, 4, 5, 6, 7, 100, 1,000, 1,000,000. This is a very steep slope right here. In fact, the closer we get to vertical, the steeper the slope. It's going to go to infinity. So the slopes of our line there tend to infinity as our angle opens up all the way to pi over 2, but not including pi over 2 because the slope of a vertical line is undefined. So we get all positive slopes from an angle of 0 all the way to an angle of around 90 degrees. Then when you go beyond pi over 2 or 90 degrees, all of a sudden the slope of this line now is negative, super negative in fact, like really, really negative. If you're falling down a mountainside like that, that's pretty much almost vertical. The slope is negative like 1,000 or maybe negative 1,000,000 or something like that. And then as you make it more shallow, it becomes less. So here's a slope of -1 maybe, and a slope of maybe a -1/2, and a slope of -1/10, and eventually it gets back to a slope of 0. Well, once you get to here, wouldn't you agree that the slopes start repeating from the beginning because it's the same lines, right? Like this line right here is, so again, we've gone a little bit past the 180 degree mark or pi mark, yet that line is the same as the line had we been facing this angle right here. So all of a sudden, once we get past 180 degrees, we start repeating our conversation, and there's no point for that. There really is no point to repeat our conversation once we have gotten past 180 degrees or pi. And so therefore, and again, this is not a proof, but a justification. Therefore, the values of the tangent begin repeating in a cyclical fashion once you go beyond 180 degrees or pi. And that is why the period of the tangent is pi. And by the way, I'm not going to do it for the cotangent, but the period of the cotangent is also pi. We'll see it in their graphs anyway, so that's not going to be a big deal. All right. That's all I have to say about that. Now we're going to begin building the graphs of the tangent and cotangent here, but it is very important that you have already watched my video on building the graphs for the secant and cosecant, because I talk about the ramifications of division by 0 there. Not only do you get undefined numbers if you divide by 0, but depending on how your how close that denominator is to 0, the fraction 1 over something close to 0 is actually infinite, or maybe negative infinite. So please watch that video if you did not see that. So let's start with the easier of the two, the tangent graph. And this is also the most common of the two functions. So y is equal to tangent. And I'll say tangent of x because we're going to be graphing it. So we need an x-axis and a y-axis. And the way I'm going to graph this is I'm going to look at the graphs of the sine function and the cosine function, because that's exactly what the tangent is. It's the ratio of the sine to the cosine. And actually, now that I think about it, I'm not going to go about it that way, because remember when we said, oh yeah, the tangent of the arc length is equal to y over x? And then we just did that whole conversation about the slopes. That is actually a much, much easier way to graph this. So if you consider the tangent just to be the slope of the line segment along the unit circle, that's actually a much better way to graph these now that I thought about it. So let's go ahead and just graph out an XY axis, and then we're going to pop back over to that other page and refer to it for help when we graph. Now I've plotted out the XY axis, and I've plotted some dots in there that I'm not going to label yet until we start discussing the actual graph. So let's go ahead and now discuss the actual graph. All right, I decided to make a little Desmos applet instead. Now remember, the tangent is just a slope of this purple line here. As we move this angle open, the slopes will start to increase. Let me go ahead and just press play a little bit. You can see the slope here is probably not too large, maybe a 0.1 or something like that. And this is what's plotting. That black little piece right there is plotting out the slopes. So as this purple line increases in slope, the black line is just plotting those slopes. So as we get to maybe right about there, the slope is almost 1. In fact, it's going to be 1 right about there. Because again, the ratio of y, which is 0.7, to x, which is almost 0.7, is almost 1. And notice that's what that black curve is almost a y value of 1. And as this slope of that purple line increases, Well, the black line continues, or the black curve, sorry, continues to increase in its y values. So I keep increasing the slope, and you can see the black curve keeps rocketing up. Keep increasing the slopes, the black curve keeps rocketing up. Because if you think about it, the slope of this purple line now is really, really large. It's around, I'm going to say 9 or something like that. And so if I zoom out, yeah, the y value is roughly around 9, maybe 10. And so you can see that our slopes are starting to really rocket up. Now I'm going to zoom in a little bit here and maybe press play for a second or two more. There we go. And now we have a very steep slope. Let's see what the y values for our curve look like. They're pretty far up there. And eventually the slope will get so steep that it'll be infinite. And so I can't really pause it at that, because all of a sudden on the other side, once it continues past the angle of pi over 2, so that's what this purple line has now gone, or that point right there has gone past a point of angle of pi over 2. Now this purple line has a very negative slope. And a very negative slope means, if I zoom out far enough, you can see we're plotting some very negative y values for our tangent. So let's go ahead and zoom in again. I'll press play. And you can see these are all negative slopes, but it's eventually going to have a slope of -1. And as it gets to that point, you can see the behavior of the tangent curve starts to take shape. Slopes are negative, 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 negative. They're about to be a slope of 0. Now they're a slope of 0. Now they're positive, positive, positive. There'll be a slope of 1 in a moment. There we go. And then slopes increase infinitely. And then all of a sudden they pop over and become negative infinite slopes. And then they increase. Now they're -1. And then the slopes become almost 0. Now they're a slope of 0. And now I have it going backwards now, but anyhow, so that's the graph of the tangent function. And if you went the other way, if I unwound this, you see the slopes are negative. They get to negative infinity. And then now the slopes are very positive. When I say the slopes, I mean of that purple line on the unit circle. And you can see the tangent curve carves out. And if I turn on the tangent, this is the tangent. Notice where we're going to have issues with the tangent curve. We're going to have an issue when the, let me move this over here. When you have a nearly vertical line, when you have a nearly vertical line here. So in other words, at the angle of pi over 2, or the angle of, sorry, that wasn't an angle of pi over 2. This is an angle of 0 roughly. This is an angle of pi over 2. Here's an angle of negative pi over 2, where it's almost vertical. Here's an angle of 3 pi over 2. Here's an angle of negative 3 pi over 2 right there. Actually, this is negative 3 pi over 2. So anyhow, any odd multiple of pi over 2 in the tangent's going to have issues. And that comes from the fact that the cosine actually has issues at, or doesn't have issues, but becomes 0 at odd multiples of pi over 2. If I were to graph the cosine on here, which is the denominator of the tangent, you will be able to see that every time the cosine crosses the x-axis is when our tangent has an issue. In fact, if I were to graph x equals pi over 2, you could see, and then maybe I should also graph x equals 3 pi over 2, just so you could really see it. And I'll make them both red just so that you can see that they are asymptotes, and I'll dash them out. Why not? There we go. You can see that's where our tangent has vertical asymptotes, is at pi over 2 and 3 pi over 2, and then 5 and 7 and 9 pi over 2, -1 pi over 2, -3 pi over 2. And that happens exactly when the cosine crosses the x-axis. So again, going back to our paper here, we know that the tangent curve, well, it's going to give you the slopes of your line segment on the unit circle, and it's obviously the slopes are going to be positive as you approach the angle of pi over 2. So this is the angle of pi over 2. Notice that I'm writing x equals pi over 2 because, well, that's when the tangent has that issue. And then once you get beyond pi over 2, all of a sudden the slopes are incredibly negative. And that's because on that circle, if you are beyond the angle of pi over 2, you have these very negative slopes on that line right there. So that's why the tangent's negative and near to negative infinity when you're on the other side of pi over 2, the right-hand side of pi over 2. So I'm just going to graph that in here. Whoops, wrong ink. So let me go ahead and do that. And it climbs up, crosses through here, and climbs all the way up there. And again, remember what I said in the animation there. It's at every odd multiple of pi over 2 that you have that division by 0. And so at pi over 2, 3 pi over 2, and negative pi over 2, and negative 3 pi over 2. There you go. And it is an odd, tangent's an odd function, so I could just copy my graph, spin it about the origin here, and copy the graph, and you will get the entire, well, at least a representative example of the tangent curve. Okay. That is, and it goes on forever, okay, but that is the tangent. Now, something that I should mention here is when we go to start graphing transformations of the tangent, I used to teach, and I know a lot of textbooks do this, they teach graphing the base graph from negative pi over 2 to pi over 2. That would be tragic. That's bad news. You want to graph the base graph from 0 to pi. That's what this value is. So you want to graph our, and I'll just, trust me, I will showcase that when we get there. But it is very important to graph from 0 to pi, the base graph. If you don't do that, there's going to be issues with your horizontal compressions or stretches. That's just massively important. So there is the tangent graph. I'm not really going to go into that much detail about the cotangent graph because it rarely comes up. But I will go ahead and just state the cotangent is cosine over sine. And so you're really worried about that denominator becoming 0. If you just quickly graph out the sine curve, you'll see that it becomes 0 at any multiple of pi, any integer multiple of pi. So we know we're going to have vertical asymptotes for the cotangent at integer multiples of pi. So if I quickly graph here the x and y axes, and if I go ahead and label on there all these, the critical numbers that we normally have, and let me just label this the x-axis. There we go. Again, we're worried about division by 0, and that occurs at integer multiples of pi. So I'm going to go ahead and graph in here the vertical asymptotes at integer multiples of pi. That's 0 pi. For some reason, that's just not working for me. There we go. 0 pi, 1 pi will be another vertical asymptote. And again, that's for some reason not working for me. There we go. And then 2 pi is another vertical asymptote, and so on and so forth down the line. So at least we get the behavior of the asymptotes just from the fact that we know the sine function crosses the x-axis or becomes 0 at any integer multiple of pi. From that point forward, we just have to think about, well, where does the cosine become 0? Because the cosine is a numerator, and the cosine becomes 0 at any odd multiple of pi over 2. And so at all of these odd multiples of pi over 2, our cotangent curve will cross the x-axis. So I'm just going to bold those in. I think I already did. There we go. And then finally, I'm going to go ahead and just state that when you have angles between 0 and pi over 2, everything's positive. So that's probably the easiest way for me to justify that the curve looks like this. And then once you're beyond pi over 2, the sine is positive, but the cosine is negative, so the cotangent is going to be negative. And then between pi and 3 pi over 2, the cosine and the sine are both negative, which means cosine over sine is positive. And you can see the pattern's just going to repeat like this. And again, it is an odd function, so if you stuck a pin right here and rotated 180 degrees, you'll get the same picture back. There we go. So this is a graph of the cotangents shifted from the tangent by a pi over 2, and it is also upside down from the tangent. So it is not a very common function to graph. Okay, so just a heads up, it's not a common function to graph. That's all I need to really say. So in the next video, we're going to go ahead and graph these, and I will, yes, graph the cotangent function. But again, you're not often going to be asked to graph the cotangent. Tangent, on the other hand, does get graphed, but the cotangent, not very often.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Just listen close. Don't talk too much that isn't cold. Sure, you may really hurt inside. It doesn't justify you to speak too loud and cry.